Welcome everybody to this talk on macroscopic quantum systems. It's a rather new field of research in physics. Most likely all of the important results in this field occurred in the last 10 years. So it was actually very fortunate timing for me to be doing my postdoc in this field of research. And so I want to start by saying that almost everything that I present in this talk is based on research I did at ETH Zurich in Switzerland. And this was in the group of Professor Lukas Nowotny. And a lot of this work was done by the PhD students, Johannes Piotrowski and Dominic Windy. Very recently, I moved to the University of Manchester in the UK. And I have started building a lab that follows similar tracks of research in macroscopic quantum systems. So it's going to be a fairly general talk. I'm not going to go too much into the technical details. If you want to ask questions and talk more in detail about the specific results, please just contact me independently or ask questions at the end of the talk, and I'd be very happy to go through them. So you don't really need to know what macroscopic quantum systems are or optical tweezers to understand what's going on here. So let me start by telling you a little bit about where I'm based right now. So this is the University of Manchester. It's in Manchester, which is almost halfway in England, in the middle of England. And there's a lot of history in Manchester in science. For example, this is where Rutherford split the atom to find out that it's made of a positive nucleus and electrons around it. It's the place where Alan Turing invented the first versions of what is today modern computers. But perhaps you might have heard about the more recent research in Manchester regarding 2D materials, specifically graphene. The Nobel Prize in 2010, for example, was awarded for the invention of graphene that happened in the building right next to where I'm sitting. And today there are a few different research institutes and centers that are in this area of material science, advanced materials, photonic science, including biophotonics, and also more recently quantum science and engineering. And I personally, I am based in the Photon Science Institute, affiliated to the Center for Quantum Science and Engineering, working on quantum photonics. And so if you are interested in getting in touch with any of the people here in Manchester doing research in material science or photonics or quantum science, please get in touch with me. I'll be very happy to connect you with the appropriate person in Manchester. Okay, so coming to the scientific content of my talk, I'd like to start with an experiment that everyone who studied physics is familiar with, which is the famous experiment in the 1800s by Thomas Young, where he used a point-like source of light, and then he propagated it to a double slit, and he was able to observe an interference pattern on the other side. And this was one of the first experiments that made people believe that light is a wave, and all of its physics can be all physics to do with light can be described by thinking of light as a wave. And it took 100 years before proposals were made which said that, hey, maybe it's not enough to think of light as waves in all situations. There might be some situations where you need to think of light as bundles of energy that are in discrete multiples of the wavelength of the light that is used. And a very famous example of this is the photoelectric effect. And these experiments made it clear that in certain situations, it's not enough to think of light as waves, but you really need to think of the particle nature of light as well. And there's a very similar story for matter, where initially people thought that matter is made of particles. An example of this is the Rutherford experiment with the gold foil, which made him conclude that there's positive nucleus and electrons that are negatively charged going around this nucleus. And so everyone thought that matter is made of particles. It was only a few decades later that it was proposed that particles are actually bundles of waves. This is Louis de Broglie, and he proposed this famous de Broglie wavelength associated with every matter particle, that in fact there might be situations where you cannot describe matter as just being discrete particles, but you need to take into account the wave nature of particles as well. And one of the first experiments in this direction was when people repeated very similar experiments to Thomas Young's experiments with light, but with a point-like source of electrons, a matter particle, and used this electron source, propagated it to a double slit, and they were very surprised to see that there's actually an interference pattern which is indicative of wave nature also for matter particles. And this is a time lapse of the screen where the interference pattern is observed, where if you send electrons one after another, even though they appear at random points in the screen, if you average over a long period of time, there are clear bright and dark fringes where dark where electrons never end up, and bright where a lot of electrons end up. And perhaps you're aware of this, perhaps you're not aware of this, but this has been a field of research by itself where people have tried to demonstrate quantum properties in material systems in larger and larger or heavier masses, larger and larger length scales, starting with the 1927 experiment with electrons in double slits, followed by neutrons, which are heavier than electrons in 1936, and then to an alkali atom, and very famously Buckminster fullerene, which is carbon-60. It's a sphere of carbon atoms. It was also put in a superposition it was put in a superposition, so the wave nature became clear when they observed an interference pattern after sending Buckminster fullerenes through a double slit. And even in the last 20 years, a lot of research has been done in pushing these numbers higher and higher. Most recently in 2019, and this is current world record for the largest object that has ever been put in a quantum superposition, is a molecule that has about 20,000 atoms. And this was done in the group of Markus Arndt in Vienna. And they are pioneers in this field of research. But as you can see, like it's not very easy to keep pushing to larger and larger masses, because as the size and the mass increases, it's more likely that this particle will now start interacting with the environment more easily. And every interaction with the environment is a decoherence mechanism by which the quantum properties get lost. So you need to learn to isolate and control material objects as you go to larger and larger scales if you want to observe quantum effects in them. And in our field of research in the last 5 to 10 years, we took a different approach, which is rather than going up in this plot over here, starting from small and going to bigger and bigger particles, we start with a big particle, which you would normally consider classical, like a nanoparticle. In our case, it's silica nanoparticles, which is just glass, really. And think of these silica particles as spheres of glass, which have a diameter of about anywhere between 100 nanometers to a micrometer. So these are nano or microscale mechanical systems, and they're mechanical systems because they are, what we do here is that these nanoparticles are levitated inside a vacuum chamber using only optical fields. So you use an optical tweezer. So you have a light beam coming in from the left over here. You can't see it because it's infrared, and it's focused down to a very, very narrow waist in the middle over here. And when you have a laser beam that's focused to a narrow waist, it's called an optical tweezer. And that's where you trap the silica particle. And because it's sitting in this harmonic potential, it behaves as a mechanical oscillator as it goes back and forth in the waist of this tweezer. And so what we have prepared here are these nano and microscale mechanical systems in high vacuum. And our goal is to learn to isolate and control this now macroscopic object, which is 4 orders of magnitude heavier than the current record holder for the biggest quantum object. And try to observe quantum properties in them, such as microscopic superpositions. And the reason we want to work in this length scale of 10 to the minus 4 meters, so hundreds of micrometers to hundreds of nanometers, is that it is very clearly far away from what we would traditionally consider as the quantum world, where atomic scales, angstrom distances, nanometer distances, where atoms exist. For example, an atom is clearly a quantum system because it has discrete energy levels. On the other hand, on the other extreme, you have the classical world that we're familiar with, where almost everything can be described simply by the laws of classical physics, and there's no need to invoke quantum physics. And there's a transition from the quantum description of object to the classical description of object has to happen somewhere in this mesoscopic length scales. And that's what makes it very interesting platform to try to explore macroscopic quantum physics in these scales. So our goal, once again, is to learn to control and isolate this object such that we can show quantum science or macroscopic superpositions, reduce the decoherence such that you can then use this for practical applications such as sensing. and also in material science and equilibrium physics, non-equilibrium physics, using this unique platform that is in the middle of the classical and quantum world. And in this talk, I will primarily focus on the quantum science and sensing aspects of these levitated nanoparticles. So first of all, remember, the goal is to show wave-like behavior in these massive objects, massive because it's 4 orders of magnitude larger than the previous record holder. How do we do this? Well, de Broglie wavelength, the equation for it, he suggested that the wavelength is inversely proportional to the mass times the velocity. And as you increase the mass to larger and larger numbers, the only way to see wave-like behavior in these objects is to reduce its velocity to get the same wavelength. So if you consider a particle trapped in an optical tweezer, you have this harmonic potential. The particle has a lot of energy from thermal energy that makes it go back and forth in all 3 dimensions if you don't do anything to cool it down. But now, if you don't do anything to cool its velocity down, but you could do this by using different techniques that I will describe later, and you can cool the motion to a small enough temperature that the motion is no longer limited by thermal noise, but rather by vacuum fluctuations in the vacuum chamber, or quantum fluctuations that arise in vacuum. And the motion is driven only by that. And so if you're able to cool your nanoparticle, cool the motion of this nanoparticle, the motion being the mechanical degrees of freedom. So linear motion would be translational degrees of freedom, so X, Y, and Z motion. You can also have angular motion, where it is where the particle is kind of vibrating back and forth about a fixed axis. And the whole game, this control that we're trying to achieve, is to start with an object that is highly thermal at room temperature, to cool its mechanical degrees of freedom all the way down to what is called a standard quantum limit, where you can think of the particle as being a point-like source, which can then be used to do these double slit experiments to observe the interference pattern. And I want to point out, just to give an idea of what this is in real numbers, I need to be able to control the motion of these nanoparticles all the way down to the size of the atom. So the displacement of this object needs to be confined to a space that is less than the size of an atom to achieve this goal. So why would we want to do this? The motivation in macroscopic quantum science is to answer some very fundamental questions in physics, such as, for example, if you think of having a massive object, something that has a large mass, as being in a superposition of 2 places, what is the gravitational field around it going to be like? So if you have a single particle, it's very clear what the gravitational field is going to be like. But if you now have a superposition of the object being in 2 places at once, what is the field going to look like in the near field, in the far field? How is this going to change the gravitational field? And this is interesting because there are theories which predict that the fact that an object has a large mass, that it can interact gravitationally, will automatically collapse the wave function and prevent macroscopic superposition from being formed. So by performing these experiments and trying to observe macroscopic superpositions, we can put bounds on these theories that describe wave function collapse due to heavy masses. Another one would be if you have multiple particles, and you can try to entangle the mechanical degrees of freedom. And finally, you can use it as if you have now a 2-dimensional array of particles or 1-dimensional array of particles, it becomes this very nice many-body physics simulator, where you can now think of engineering different interactions between different particles, such that you create an interaction map where you can fully tune how much each particle interacts with every other particle, and study some many-body physics, some emergent phenomena that can happen with these interacting systems. And the challenge to get there, as I motivated earlier as well, is that you need to cool the motion of this object all the way down to the lowest energy level of your harmonic oscillator, which is called the quantum ground state. It's called the quantum ground state because at the lowest rung of the harmonic oscillator, your motion is limited by the standard quantum limit. And if you want to observe entanglement or study many-body physics, then it's not enough to work with only a single particle, but you need to scale up your system to have an array of nanoparticles. And if you want to do many-body physics or entanglement, you need to be able to have interactions that are tunable between different particles in your array of particles. Now, that's that's the motivation for the fundamental science. If you more recently, there's a lot of interest in building something useful, so useful quantum technology out of the quantum science research that has been happening for decades now. And one example of that is quantum sensing. Here, first of all, let's think of what I mean when I talk about sensing. So we'll start with classical mechanical sensors. You might have heard of gyroscopes or MEMS systems, which are essentially, they're also mechanical oscillators. Typically, they're like cantilevers, so they are clamped on one side and then they oscillate back and forth on the other. Or you can have a membrane, so it's like a two-dimensional layer that oscillates up and down with a certain frequency. And by this is essentially what is used in cars, in phones, as acceleration sensor. So if you take out your phone, if you open up your phone, you will see that there is something that looks like the top right picture over here, where you have different mechanical membranes that are talking to each other to extract information about how much acceleration is in X, Y, Z direction, how much is the phone rotating along the different rotational degrees of freedom. And this is, for example, it can be useful for inertial navigation. So if you don't want to rely on GPS, then you can build these kind of offline mechanical sensors of acceleration to understand how much you've traveled along X, Y, Z, how much you've rotated along the three different rotational axes and so on. And for this, mechanical sensors are great. That's why they have always been leading the commercial part of sensing, of acceleration sensing, because they're compact, they're very small, micrometer size, they have high mass, and high mass means better acceleration sensitivity. They're also a mature technology, and they can be fabricated with very low cost. But the difficulty is that it's very difficult to make these MEMS systems behave quantum mechanically, because by construction, they are always clamped on one end, or clamped, if it's a membrane, then it's clamped on many different sides. And every time there's a physical clamping mechanism, it adds a channel of decoherence, a connection to the environment. And so it becomes very difficult to prepare quantum states of these resonators, because some of the information of the quantum system leaks to the environment, resulting in decoherence. And what that means is that it's very difficult to put one of these resonators in a macroscopic superposition or to entangle them. And that limits the sensitivity to the standard quantum limit. You cannot do better than, you cannot use quantum resources in these systems very easily to achieve improved sensitivities. On the other hand, recently there have been quantum sensors, which are typically consist of atom interferometers. And these are atoms, clouds of atoms that are levitated in a vacuum chamber using optical fields. And here, once again, the levitation allows you to overcome decoherence, because you're not physically clamped to anything, you're just held by optical fields in vacuum. And this provides direct access to quantum resources such as superposition. Just drop your cloud of atoms and then it expands as it falls down. And you can use this to do interferometry. But the limitation there is that even if you have a cloud of 1 million atoms, which is typically the upper end of what these atom interferometers can do, the mass of 1 million atoms is not very high. It's a very low mass, which means that the acceleration sensitivity is quite low. And as you can see here, these devices are not very compact. They are about the size of a human being, and they are extremely complex. And at the moment, they're still very high cost and not very competitive. So what we are looking for is to combine the advantages of compact high mass systems with the access to quantum resources. So can we use these? Can we use a different kind of mechanical systems where they're not clamped to such that we can still access quantum resources with mechanical systems? And that's where these optically levitated nanoparticles come in, because they are optically levitated, they're not clamped. And what that means is that the mechanical degrees of freedom, the motion of the particle, can be used to read out many different kinds of external forces. So if you have an acceleration, that's going to have a signature on the motion of the particle. If you have an electric field in the background and your particle is charged, then your particle's motion is going to react to the external electric field. It could be a magnetic field. It could be just impact from a different particle. And all of these makes this untethered high mass mechanical sensor very good as a sensor that could access quantum resources. So I'll just run you through a few examples of what I mean by sensing here. So you can imagine, if you imagine you have a car or a submarine that you want to track without GPS, in how much it's moving in linear direction and in angular direction. So typically, if you turn left, then it's a signal that is temporal, which means it's not a constant signal, but the acceleration only happens when you turn left. So it's kind of an impulse type force. And if you now had a nanoparticle that was cooled to a very low temperature, then as the car moves to the left, the motion of the particle is going to get affected because there's a change in the velocity, and therefore the energy of this oscillation is going to change. It's going to gain some energy. And if you're able to detect these small changes in energy, then you can use it to extract small accelerations of the system that this nanoparticle is in. So what is crucial here is that the particle needs to be cooled to a very low temperature. If it's not cooled to a very low temperature, then you're trying to look for small changes on top of a particle that already has a lot of energy, which is very difficult to do. So if you want to measure small changes, you need to go to an extremely low starting point temperature, and then you can measure small changes in this energy due to an impulse force. Another example is a constant force. If you want to measure acceleration due to gravity, for example, if you want to measure static electric or magnetic field or pressure, then these are constant signals. And for this, you can do a different kind of protocol where you now have a particle that's moving back and forth. Then you can just turn off your light field, which means that the particle is freely moving in response to the external force, and then recapture the particle. So turn on your optical field again and see what the influence of the external force was in terms of how it's changed the position or energy of the object. So for example, I have a particle that is localized here in the left peak over here, and then due to an external force, when the trap is off, it moves due to the external force. Then when I recapture it, I can note that its position has changed, and by measuring these small changes in position, I can use it as a readout to extract this constant force. And I just want to point out that this is impossible to do with traditional mechanical sensors, because in a MEMS or a gyroscope, you cannot just turn off your trap, because your trap is the clamping mechanism, and you cannot remove and turn off and turn on your clamping mechanism in mechanical sensors. That's the advantage of these levitated mechanical sensors. And finally, it can also be used, very recently been proposed in use for the search for new physics. And this could mean you bring two nanoparticles that now have mass close together to distances that are of the order of micrometers in vacuum. So it's a very clean system where you can bring two massive objects together, turn off the trap, and see if there are any interactions between the two particles that cause a change in position or energy of these particles when they're recaptured. And you can use this to measure deviations in short-range forces. For example, if you think of Coulomb forces or gravitational forces even, you think of it as an inverse square law. But is this an approximation? Are there dependencies that are 1 over d cubed or d to the power 4 that you cannot measure because you don't have clean enough systems where you can bring charged particles or heavy particles in a vacuum chamber to distances that are of the order of micrometers? And also it can be used for detecting particles. So for example, if you want to build a high frequency gravitational wave detector or a dark matter detector, then the fact that you have these oscillators and they have a certain oscillation frequency, and the oscillation frequency can be tuned by changing the optical power of the beam. In situ, you can change this continuously as you want, and this changes the resonance frequency of your sensor. And so you can use this as a tunable detector for gravitational waves as well. And once again, for sensing applications, the challenges are exactly the same as for fundamental science applications, such as macroscopic superpositions. You want to start with an extremely cold temperature of motion. So you want to cool the mechanical motion of the oscillator all the way to the lowest rung of your harmonic oscillator, the quantum ground state. And if you want to do these kind of experiments that are in search for new physics, or even for inertial sensing and for gravimetry, you can improve sensitivity by scaling up to not just one particle, to go beyond a single particle to an array of particles, to improve your signal-to-noise ratio or to operate at many different frequencies at the same time. And also it helps to engineer interactions between particles, because then you can make use of collective effects like synchronization or entanglement to boost your sensitivity further. Okay, so in the next 10 to 15 minutes, I just want to summarize some of the main results that have come about in this field that go towards the direction of addressing these challenges. One is quantum ground state cooling, one is scaling up to particle arrays, and the third one is engineering tunable interactions between nanoparticles. So first one, how do you ground state cool a particle? So you can think of what I just said before as you have a silica particle that's held by an optical tweezer, a focused beam of light, of laser light with a certain frequency. And now this particle is going to scatter some of the light from this tweezer in many different directions, in all different directions. Well, first of all, this particle is sitting in the harmonic potential that is created by the optical field. And initially it has a lot of thermal energy, so it's just going back and forth with high energy. And the goal is to make the motion of this particle restricted to the lowest line over here, so the quantum ground state of this harmonic potential. So the optical tweezer traps the particle scatters light from this tweezer in all directions, and I can now collect the light that is scattered by this particle using a cavity. It's a Fabry-Pérot cavity, it's just two mirrors that is initially unpopulated, so it gets populated by the light scattered, the tweezer light that is scattered by the particle. I can send it to a detector, and if I measure the output of this detector, what I would see is 7 different peaks, where if you just ignore the fact that there's a cavity now and it's just light scattered by this particle from the tweezer hitting the detector, you would see a line at 0 frequency here, which corresponds to all the scattering events, which did not change the energy of the photon. So the input photon energy is the same as the output photon energy, and that's the peak corresponding to 0. That's Rayleigh scattered light. But you also have Stokes and anti-Stokes sidebands to the Rayleigh scattered light, and this comes from the fact, for example, the left 3 peaks over here come from all those scattering events where the photon coming out, so the photon that is detected, has a lower energy than the tweezer light. And if the photon coming out has lower energy than the tweezer light, that means that the particle has gained energy from the tweezer, and the energy has been transferred to the mechanical motion. On the other hand, these 3 anti-Stokes peaks, they correspond to all those scattering events where the photon that comes out has a higher energy, which means that these correspond to scattering events where the particle, the light field has taken energy away from the particle motion. Effectively, it has cooled the motion of the particle. And what we do with the cavity, we now introduce a cavity such that it enhances all those processes. So these 3 peaks, the anti-Stokes sidebands, which take away energy from the particle motion, and it suppresses all those scattering events, which add energy to the motion of the particle. So effectively, you're using the cavity as a refrigeration tool, where you enhance the cooling rate and you reduce the heating rate of the particle. And just to remind you, the reason there are 3 peaks on either side is because the particle is moving along X, Y, and Z directions. And so these are the peaks corresponding to the different degrees of freedom, linear degrees of freedom. And so, yeah, so when you add this cavity, you get an enhanced cooling rate as opposed to and a reduced heating rate. And so you can use the height of these peaks that you measure in your detector as a way to extract the temperature of the mechanical motion of the particle. It's called sideband thermometry. And so we do this experiment now, and we measure the experimental data, and we see that as we tune the detuning of the cavity is telling you how much is this value delta. Where is the peak of the cavity transfer function, the blue curve, with respect to the Rayleigh peak over here? If delta is 0, it means that you have equal number of Stokes and anti-Stokes photons. You're not really cooling or heating the particle. But as your delta approaches the mechanical frequencies of the degrees of freedom you want to cool, you maximize the cooling rate of those modes. And as the particle gets cooled to lower and lower temperatures, the energy in the motion goes down, which can be observed as you see this peak. It goes down as you go closer and closer to to resonance with the particle motion. So the darker blue is getting closer and closer in resonance. And the reason the peak goes down is the area under the peak tells you how much energy is in the degree of freedom. So as the peak height decreases, it means that the energy in the motion is also decreasing. And so, yeah, we do this for 2 degrees of freedom, and we see that at our optimal detuning, the energy, so the N over here on the y-axis corresponds to it tells you which rung of your harmonic oscillator you're sitting in, and your goal is to get as close to 0 as possible. So by doing this cavity-based coherent scattering cooling, we're able to cool both degrees of freedom of motion, linear motion, down to the quantum ground state, which is defined as anything less than n equal to 1. So a value of 0.8 means that 20% of the time the particle is in the ground state, and 80% of the time it's not. Okay, and so what this means is that we have taken an object that had thermal motion corresponding to room temperature and used this cavity to refrigerate, to cool the motion all the way down to your point-like source that you can now use for your experiments for doing macroscopic quantum science with it. And again, to give you the scale, what we do in real terms is that the motion of this nanoparticle is about 200 nanometers in size. Its motion is cooled to something that is tens of picometers in length, which is quite impressive. And we are able to do this along 2 dimensions at the same time. And in fact, this is not restricted only to linear motion. I can also very well cool the angular degrees of freedom. So if my particle is vibrating about a fixed point, then I can also cool the mechanical degrees of freedom corresponding to such oscillations. And they typically happen at larger frequencies, so megahertz frequencies, and even that can be cooled to the quantum ground state of motion. So I will spend a few minutes now in talking about another experiment where, so you've seen so far how you can use a single tweezer to trap a single particle. And the question is now, how do you scale this up to arrays of nanoparticles if you want to study entanglement with it or many body physics? Well, then we took our solution from the atomic AMO community, the atomic and molecular physics community, where there's been tremendous progress in working with arrays of neutral atoms using these devices called acousto-optic deflectors. And they're essentially, there's a crystal inside there. You send in different radio frequency inputs. It creates a standing wave in the crystal. So when you have a beam of light coming in, it gets deflected by an angle and also in frequency, which corresponds to the radio frequency tone that you send in here. So if you just have a single beam and nothing, no input over here, then the beam is just going to come out on the other side. But if I now send in a beam that is, an RF input that is at 40 megahertz, then I'm going to get a beam that is deflected by a certain angle and shifted in frequency by 40 megahertz. And I can then send that beam to the vacuum chamber to trap a particle as illustrated here. Now, nothing stops me from sending 2 different tones, so 40 megahertz and 60 megahertz. Then I get another beam coming out, and I can send them both to the vacuum chamber. And I can keep adding more and more radio frequency tones to generate an array of tweezers to trap multiple particles. And one of the best quality of this is that I can control in situ what the trap frequency is. So what is the resonance frequency of this sensor or the oscillator by simply changing the amplitude of the radio frequency input that goes into this device. So if I send in a large amplitude, it's going to be a very sharp trap, very deep trap. And if I send a low amplitude of my RF tones, it's going to be a very shallow trap. And finally, I can also change the frequency. So by modulating the frequency of this input, what I'm doing at the end is I'm changing the angle at which these beams come out. And a different angle means it's going to follow a different path, which eventually in the vacuum chamber results in a different position of the tweezer. So by changing the radio frequency, the frequency of the radio frequency, I can change the position of these 2 traps in situ inside the vacuum chamber. So I can control the interparticle separation. So I build this experiment. I have 2 different frequencies going inside a vacuum chamber. I trap 2 particles. Looks like this. When I take a camera picture, you can see 2 particles. They're separated by a few microns. And then I can measure the motion of these particles along X, Y, and Z degrees of freedom, where you will now see that the 3 curves in red, which correspond to the X, Y, and Z motion of one particle, and 3 curves in blue, which corresponds to the x, y, and z motion of the second particle. And so what this detector is actually seeing in real time as a function of time is it's seeing an oscillation signal that's going, that is periodic in time. And so this detector is called a quadrant photodetector because it's not just a single detector chip. It's like an X shape. So there's 4 different quadrants of detectors, 4 different detectors. And so if my particle is moving left and right, then the light scattered by it also moves left and right. And so the signal on the detector between the left and the right detector is going to oscillate at the same frequency as the motion of the particle. So that's what you see over here. The particle is in the left over here, on the right over here, left, right, left, right, left, right. And you can use this as a way to extract the frequency of oscillation along the x degree of freedom by taking the Fourier transform of this time signal, which is what is shown over here. You can do the same for the y degree of freedom and the z degree of freedom as well to extract all 3 degrees of freedom of motion, of linear motion of these 2 particles. And now we thought it's nice that we can detect the motion of these different particles, but can we also use the fact that we are measuring in real time the motion of these particles to cool the motion of the particle? And this is a solution we came up with, which is you have this detector that's detecting the time signal of this particle motion. Can I send a feedback to my input laser field to cool the motion of the particle? And it works like this. So imagine the following. If my particle is moving left and right, and every time it moves to the left, I damp its motion by moving the tweezer to the right, such that the particle gets pulled to the center of the trap. And when the particle moves to the right, I move the tweezer to the left, such that once again, the particle motion is damped. And what this means is that I'm shaking the optical tweezer at the same frequency as my particle, but with opposite phase, such that when it moves left, I move the tweezer to the right. When the particle moves right, I move the tweezer to the left. And it needs to be in the opposite phase, such that I end up damping the motion of the particle. If it's exactly in phase, then I end up amplifying the motion of the particle, which is not what I want. I want to cool the motion, so I apply it out of phase in this feedback loop. I can also choose the gain, which tells me what is the amplitude by which I shift my tweezer. And I can send these as input to my radio frequency input. And in situ, I can control the forces that are felt by this particle and end up cooling the motion of the particle. And it works like this. So I have a particle, it moves back and forth. I measure in the detector. I send a feedback signal. And you can see the experimental data that as I increase the gain in the feedback loop, which corresponds to the displacement of my tweezer when I shake it, the area under this curve goes down, which means that the energy and the temperature of this particle motion is decreasing. And yeah, you can see this in this plot as well. As I increase the gain, the feedback gain, I get lower and lower temperatures until I reach a point where the signal goes to the noise floor, and then I'm just feeding back noise into the system, and I cannot cool the particle anymore. And it hits this, that's the lower limit that you see over here. And the cool thing about this technique is that I can just scale it up to as many particles as I want. If I now have 2 particles, I just need to send the output of the detector to 2 different channels of to 2 different radio frequency inputs into my acousto-optic device. And by choosing the right gain and phase of my feedback, I can end up cooling the motion of both particles simultaneously. And so this is it's a scalable cold damping technique, which I can use to cool an array of particles simultaneously, which is important for doing all of these many body physics and entanglement with nanoparticle arrays. I think I have a few more minutes, so I will go to the last part, which is about, so far you've seen how you can ground state cool. So you reduce the temperature of mechanical motion of a nanoparticle, of a mechanical resonator, all the way to the quantum ground state, where its motion is limited by the standard quantum limit. And this is a good starting point for doing these experiments where you can now, this is like your coherent source, as you had in the case of Young's double slit experiment, or your electron gun in the experiment with the electron diffraction. So by ground state cooling the nanoparticle, I've created this coherent source of nanoparticles, and then I can, that's what you saw in the first part. And that's the starting point for doing these macroscopic quantum physics experiments, such as sending it through a double slit and looking at interference patterns. And then we saw how we can use optical tweezer arrays using acousto-optic devices to work not only with single particles, but control and cool multiple particles simultaneously. And now we go to the third part, which kind of brings both of them together. So what happens if I have an array of particles and I put a cavity around them? Can I use this cavity to make these nanoparticles talk to each other? Can I make them interact? Because so far, the particles are not interacting. They're just in two different tweezers, and they're just exhibiting their own independent motion. But can I now extract collective degrees of freedom by engineering interactions between these particles? And yeah, so the question is, how do you engineer long-range interactions between two nanoparticles? And we do it by adding another acousto-optic deflector here in an orthogonal direction, and then sending two different tones to each of these acousto-optic deflectors, such that I get a two-dimensional array. I'll just skip through this very briefly. The main point here is that when I send 4 different radio frequency inputs, I get many beams that come out on this plane. I get 9 different optical beams, but you will notice that 2 of them have exactly the same shift in frequency. They're both 100 megahertz shifted, and therefore I can use both of these beams to trap 2 particles inside the vacuum chamber and have them both resonant with a single cavity mode. So that's what I do here. I select only those 2 beams. I send it into the vacuum chamber, and I have a cavity there. And what happens essentially is that particle 1, the one on the left, it interacts with the cavity, so it's scattering light into the cavity. Particle 2 also scatters light into the cavity. And because they're both scattering light into the same cavity mode, it creates this effective interaction between the 2 particles that is mediated by the cavity mode. And mathematically, this is what the equation looks like. It's essentially telling you that the effective interaction between 2 particles is directly proportional to the product of the interaction of each particle independently with the tweezer. So this is the small g is the interaction of each particle with the tweezer. G1 is particle 1, G2 is particle 2 interaction. And it creates this effective coupling between these 2 particles mediated by the cavity. And so once again, I can send the output of this cavity to a detector. I would see a signal which looks like this, where you have 6 peaks, 1, 2 over here, and 4 over here. And these correspond to, so all the ones that are labeled 1 correspond to the X, Y, and Z degrees of freedom of particle 1. And the ones labeled 2 correspond to X, Y, and Z of particle 2. And so for the rest of this next couple of slides, I'm just going to focus on the 4 X and Y peaks of the 2 particles. And I'm trying to look for interactions between the particles. And typically, an interaction between 2 mechanical oscillators is indicated by an avoided crossing as the 2 oscillators come close to resonance with each other. So when they're close to resonance, you see that rather than crossing, they avoid crossing. And that means that the 2 particles are interacting. And so this is the kind of experiment I will do now. So I will take these 4 peaks that you see here. They are now on the, flipped by 90 degrees. So this is a spectrogram where the starting point here are those 4 peaks. And I'm now going to increase the power of one tweezer and decrease the power of the other tweezer such that they both come into resonance with each other. And as what you see here is that the lines are just crossing each other, which means that there is no interaction. And what I'm looking for are curves like this, where they don't cross anymore, but they avoid crossing each other when they come close to resonance with each other. And the reason you see them crossing here is because the interaction depends on a lot of parameters that I've listed over here. There's more, but these are a list of parameters that affect what is the interaction strength of the 2 particles. And for this particular graph, I've just chosen a situation where there is no interaction between them. And therefore, you see that the lines just cross. And then I try to go to the parameter space where I expect maximal interaction, which is when I have both the particles scattering into the cavity mode, and they have exactly the same optical frequency. Then I see that there is an avoided crossing. So the difference in these 3 plots is the detuning delta, which is the detuning of the cavity with respect to the Rayleigh scattered light of the of the tweezer as we had in the first experiment that I described. So I'm changing the power difference between the two. So where there's power difference 2 between the two is 0 is where you expect the resonance to be. And you see that when the detuning is far away from resonance, they're almost crossing. But as you get closer and closer to resonance with the particle, there's a large avoided crossing, and the separation between these two peaks here indicates the strength of the interaction. So the strength of the interaction is dependent on the cavity detuning as well, and we can get quite some strong coupling between those two particles. And we can now study what is the distance dependence. So I can use the fact that I have these controls to move. I can keep one particle fixed and move the position of the other particle along the cavity standing wave to see what the interaction between the particles is going to do. And I see that as I move the particle through the cavity standing wave, I have this periodic dependence of my interactions, and the coupling strength over here is significantly, it's orders of magnitude higher than what you would expect due to short-range interactions, such as Coulomb interactions or just optical binding because the particles scatter light towards each other. And that's the dashed line over here. But what we see in our experiments is that the interactions that we observed, because they're mediated by the cavity, they're enhanced by the Purcell factor. So the number of times the photon goes back and forth in the cavity to result in a much larger interaction strength than you could have with short-range interactions. And finally, all I showed you now was 1 degree of freedom that was avoiding crossing. But in fact, I can change the parameter such that I can choose which mechanical degree of freedom, is it X, Y, or Z, that interact with each other of the two particles. So for example, in the leftmost plot here, the Y degrees of freedom is just crossing, which means there's no interactions. But the Z degree of freedom is avoiding crossing, which means there's a strong interaction between the Z degree of freedom, but nothing in the Y. But if I change the position of the two particles along the standing wave, so I keep the distance between them fixed and move them both along the standing wave, then I can choose situations where the Z now is crossing, which means no interaction, and the Y modes cross with a very large magnitude here, which means that they are strongly interacting. So by tuning the position of those two particles, I can also tune which mechanical modes are interacting of the two particles. And so with that, I just want to give a little bit of an outlook, which is I showed you how you can ground state cool particles, how you can scale up to arrays of particles, and how you can now engineer interactions between them as well. So this is a good starting point to now consider how to do these double slit experiments. You have to do the double slit part, which in our case would correspond to getting some sort of discreteness in the mechanical degree of freedom, because everything I described so far, the mechanical degree of freedom is a continuous variable. And you need to get a discreteness in this mechanical degree of freedom if you want to do this double slit experiment. And one way to do that is by coupling the mechanical degrees of freedom to a qubit. If you have a two-level system and you couple the two levels of the two-level system to the mechanical degree of freedom, then you can transfer this nonlinearity from your qubit to the nanoparticle, to the mechanical degrees of freedom, and use that as your double slit to do these macroscopic superposition experiments. And what I've tried to indicate here is that it's very similar to the experiment that I just described, where instead of having two particles, two nanoparticles, you replace one of the nanoparticles with an atom, for example. And then you can use this cavity-mediated coupling to transfer the nonlinearity or the quantumness from the atom to the nanoparticle. You can also do many-body physics, where you now have long-range interactions between any subset of particles that is tunable. And if you put two particles in a cavity and you increase the coupling strength by a large amount, then you can overcome the decoherence of each of these particles to the environment. And you can use this to create entanglement between the mechanical degrees of freedom of two nanoparticles or more nanoparticles. So with that, I would like to thank the team at ETH Zurich, where most of this work was done. So a lot of it was work done by Johannes and Dominic. This is in the group of Lukas Nowotny. And as you can see, I'm just getting started in Manchester. We will be doing great science over here in the future, but at the moment, it's just an empty optical table. And we're looking for PhD students to join us. So if you know of any student that's motivated to work on the problems that I discussed earlier, anytime during this talk, then you're more than welcome to put them in contact with me. And yeah, we can discuss to see if it's possible to bring them here for doing a PhD and build these kind of experiments to both to explore fundamental science using these macroscopic systems and also to build quantum technology in terms of inertial sensors for navigation. Thank you.